Hello again, welcome back. I'm still Mr. Steele. I'm just wearing my dress clothes because I've had a site council meeting in a few minutes. I think it's less than 15 minutes away, but I wanted to attack several of the questions on the ESQ model and then hopefully come back afterwards and do at least a few more. My goal is to do this over the course of several days since our first official ESQ isn't until a week from the first week's Friday and the practice one even is on Monday. I'm figuring this timing will work out okay for most people. So when we left off yesterday, I'd done the first 5. I'm going to now be working through questions 6 and 7. I think that's all I'm going to have a chance to get to. That may even be optimistic, but we'll see what happens. So we're going to dive into the second part of this video. Got to press the button. The first of those questions we're going to look at comes from problem number 6, which involves using, selecting, and then executing the appropriate derivative rule for various derivatives. None of these are straightforward basic derivatives. They each involve one of the product rule, quotient rule, or chain rule, although there's a possibility, particularly on plus ESQs, but even on this ESQ, that you might have more than one rule to execute in one derivative. Now, in each of these problems, it's not going to tell you which derivative rule to use. You're going to have to select the appropriate procedure. So it's really imperative that when you look at the function, you inspect sort of its structure so you can decide exactly what you're going to do with it. For instance, if we look at problem A, which asks us to compute f prime of 1 if f of x is that square root curve, what we should notice is that the inside of the square root curve is a function itself. And in particular, it's a function whose derivative is not 1, which tells us that we're going to need to use the rule for composition of functions, and that is known as the chain rule. So we're going to differentiate using the chain rule. Now I could go through and do that chain rule by breaking this down, like decomposing it all the way, and doing one of those f of u equals the square root of u, and then u is equal to the radicand, 5 minus 3x to the third. But I think by the time you're into Calculus BC, you feel a little bit more comfortable with it. So I'm not going to do the slow algorithmic approach here. I'm just going to sort of do it as naturalistically as I can. So for instance, in this case, the first thing I want is the slope function. So I want f prime of x, the derivative, as it were. Well, we've got the square root of something, and the derivative of the square root of something is 1 over 2 square root of that something. So I'll fill in that specific something right there. And then we're going to multiply by the derivative of that something. Now again, if I were doing this authentically, I would just do this derivative right now. But for the sake of demonstration, I'm going to go show it with a little extra work. Now from here, the derivative of that inside is negative 9x to the second. And since I'm multiplying 1 over something times a fraction, we can imagine that over 1. Or something that's not a fraction, that we can imagine over 1. I can write this as negative 9x squared over 2 square root of 5 minus 3x to the third. And that would be our answer. We'd be finished with this problem were it not for the fact that we were specifically asked in this case for f prime of 1. So to finish this up, we need to evaluate this expression for the derivative at x equals 1. That is, we can compute the slope of the function f at x equals 1. That's going to be negative 9 times 1 squared. Obviously, again, you can simplify this faster. Over 2 square root of 5 minus 3 times, got a unicorn horn, 3 times 1 cubed. And if we clean this up, that's going to be negative 9 over 2 root 2. And this is a perfectly wonderful final answer. If you wanted to rationalize, you absolutely could. This would be negative 9 root 2 over 4. So those are probably the two answers I would be expecting. Several others are possible depending on how you represent things, whether you write things with like a 1/2 power or not. But I think these two represent the best versions. I think the most correct answer is this one. But again, correctness is a discrete quantity, isn't it? Basically a binary quantity. You either are correct or incorrect. These are both correct. So obviously, perfectly fine. Our second derivative, once again, does not tell us which derivative rule to use. We have to read the structure of the problem. And looking at this, I can see pretty clearly that I've got a function divided by another function. So I'm thinking quotient rule. Like for sure, I'm thinking quotient rule. Now, having said that, although I'm thinking of the quotient rule as I look at this, I will note that it is possible to rewrite g of x as 5x squared secant of x. So if you're just really into getting secants into your derivative rules, or into your derivatives, then maybe this is an option for you, in which case you would use the product rule. But seeing as that's not how the question is structured, and remembering the derivative of secant is likely a little bit more difficult for you than it is to remember the derivative of cosine, sort of a fundamental one, I'm going to stick with the quotient rule. We'll see if my voice works here. Also of note, we're asked to compute g prime of x, so we just want the derivative rule. We're not looking for the specific slope, so we won't have to plug in a number or anything here. We just want the derivative itself. And this does mean that we can now take the derivative. I'm going to use the quotient rule. So remember with the quotient rule song, we described the denominator as the low function and the numerator as the high function. And then we just sing it into the song if you don't remember the structure of it. So low, d high, and the derivative of 5x squared is 10x, minus high, d low, and the derivative of cosine is negative sine, so watch me just put in sine of x and change the sign. All over low, quotient rule. Hopefully you did the quotient rule part on your own at home. I was going to say I'm watching you, but I'm not. I'm definitely not. That's super creepy. I'm not watching you. But what I am watching is this function, which is, by the way, correct. Like, you could stop there if you just were that kind of person. You could stop there. But I want to clean this up just a little bit more. And by the way, when I say clean up, I don't mean dividing out a cosine. It doesn't work. That's not a thing. Don't do that. Don't do that. What I can do is I can pull out a GCF. I noticed that we've got a 5 and a 10. I noticed we've got an x and an x squared. So I'm seeing a GCF here of 5x coming out in front. Other than that, I'm going to have up top then left over, I'm seeing what looks like 2 cosine of x. I'm also seeing what appears to be x sine of x. And then down below I have cosine of x squared. So I can just write that as cosine squared. And that's exactly what I'm going to do, just to make it look as sort of clean as possible. There is the derivative answer I'd be looking for. There's what I've got. There's my stuff. So again, there's nothing wrong with this answer. This is perfectly fine. But of course, I just wanted to clean it up just a little bit more. And again, why did we not plug in a number? Because we wanted g prime of x. We didn't want g prime of 7 or g prime of pi over 2. You know what I mean? Okay, question C asks us to compute h prime of x if h of x is e to the x times tangent of x. Well, if you're a betting person, you might just automatically have gone like, well, if we did the chain rule and the quotient rule first, I'm betting there's a product rule. And yeah, this is definitely a product rule problem. But the product rule is the correct and appropriate choice here, not just as a product of the functions that came before it that we differentiated, but because specifically we have one function times another function. So basically, product rule it is. So if you'll recall for the product rule, it's basically the numerator of the quotient rule, except with a plus instead of a minus. But effectively, and I'll write it out with a little bit of structure here, we take the derivative of the first times the second, and then we add to that the first times the derivative of the second. Now, I make a big deal about potential final answers that are early in the process. This isn't one of them because there are 2 derivatives that haven't been evaluated yet, so let's do that. We'll have e to the x tangent of x, the original function, really. And then finally from there, we're going to have e to the x times the derivative of tangent, which is, of course, secant squared of x. So there is our derivative. I would say this is a perfectly great final answer. But, of course, I can see a really clear common factor of e to the x. So it'd be e to the excellent to factor that out. And when you do, you get tangent of x plus secant squared of x. And yeah, there are ways that you can break down tangent of x plus secant squared of x. In particular, if you use a Pythagorean identity, you could find a way to replace tangent. Oh, that'd be a square root. It'd be messy. Yeah, I think that's probably about as good as it gets. I guess you could do something involving a denominator of cosine, but I'm not sure it actually gets much better. So I'm going to stop right there. That looks perfectly reasonable. And it also leaves me time to do probably one more problem, which is convenient, because I think there's one more problem on this section of the ESQ model. There it is. The last one asks us for p prime of 2 for p of x equals 3x plus 5 times f of x. This one is pretty clearly going to be product rule. I think you can probably see it as well here. It's a product of 2 different functions that's being differentiated, but there's this extra complicating factor of p prime of 2, and we're given some function value things, so a lot to think about here. But as with most things, like when you run into a calculus problem that looks intimidating, if you can recognize even just one operation, oftentimes that is the most important hurdle to clear. If you even get into the problem, oftentimes there's just nothing left to do once you've done the calculus. In fact, I might say that for the non-conceptual questions on the AP exam, it typically amounts to can you access and enter the problem, and then just use the things that you're given. So this is one of those cases. Here's what I mean. So first of all, I'm going to differentiate p of x. So I want p prime of x first. That's going to be the derivative of 3x plus 5 times f of x plus 3x plus 5 times the derivative of f of x. Did I say that wrong the first time? I'll hope not. In any event, when we clean this up, this will be 3 times f of x plus 3x plus 5, that quantity, times f prime of x. So there is p prime of x. But keep in mind, we want specifically, as it says right here, p prime of 2. So we're going to evaluate both sides of this equation at x equals 2. That's of course going to give us p prime of 2, but it's specifically going to give us 3f of 2 plus what is 6 plus 5 or 11 f prime of 2. Now this could be a problem, except like they gave us values right here to use, so they're all here. We have 3 times 4 plus 11 times 6. And as a reminder, like this can absolutely be a stopping point. Like that is the correct answer. Although I don't think it's bad to finish forward. This will be 12 plus 66, which is going to be 78. So I think the most prideful answer, the answer that demonstrates the greatest pride is 78. Excuse me, the problem that respects me the most in my time is probably 78. But they're all correct. Like if you really wanted to stop on 12 plus 66, you're just like, nope. That's correct too. Good job. And that ends this first section, so I'm going to stop for the moment and go to my meeting. I'll be back in a little bit to at least do 7, maybe do 8 too. Thanks. Okay, I'm back. Meeting finished up a little bit early, so I can definitely knock out, I think, this one and maybe the next one. We'll see. So our next question we're going to look at comes from question 7. We're going to do both of the problems in here. These ask you to compute the derivative from an implicit relation. So in particular, what we're going to be seeking in this case is an expression for dy dx that is a function of the same variables that we see here. So it'll be dependent in this case on both x and y values. So in order to do this, the important thing to note is when we're differentiating this way, we're explicitly differentiating implicitly, but we're doing it with respect to x. So what you'll note in my work is I will surround, unless I'm like really trying to speed through it, I'm going to explicitly note that we're differentiating with respect to x because that clues us in a little bit as to how we're going to differentiate each term. So when we run into a term that's a function of x alone, we differentiate it like normal. So x to the third's derivative with respect to x is 3x squared, whereas the derivative of e to the y cubed power is going to be what you'd expect, 3y squared e to the y cubed, but because there's a y, there's an implied connection between x and y, so we multiply by y prime. Or you might see in some places dy dx. I just prefer not to use dy dx because it gets clunky shoving a fraction in there. So in a sense, that is really implicit differentiation right there. We're basically accounting for that connection between x and y and differentiating using the chain rule. On the other side, we have y to the 7th. The derivative of y to the 7th will be 7y to the 6th, but there is a y, so we need that factor of y prime. And of course, the derivative of 5 is 0 with respect to any variable. So effectively, there is our implicit derivative. The thing is, what we're trying to get is dy dx, which means we're trying to get that y prime factor isolated. So I'm going to do two things to make that happen. And keep in mind there are always two different ways for your answer to look that are both, equally correct, not even including stuff like GCFing out something. But effectively what we need to do is we need to get all the y prime terms onto one side. And the reason why we need that is because we want to GCF it out. Basically when there are 2 here, there's 1 in each of these 2 terms. We can GCF out a y prime and then leave us with this extra factor, 7y to the 6th plus 3y squared e to the y cubed. And now to get y prime by itself and effectively solve for y prime, also known as dy dx, we divide by this massive factor here. So I'm just going to do it this way. I'll point out then that y prime, also known as dy dx, is going to be equal to, our denominator is bigger, so I'll start there, 7y to the 6th plus 3y squared e to the y cubed. And then all of that is under 3x squared. So effectively there is our derivative. Now as a heads up, as some of you discovered when you dealt with implicit differentiation last year in the previous course, effectively this is the same answer as negative 3x squared over negative 7y to the 6th minus 3y squared e to the y cubed. Now this one you can pretty obviously see, since they're all negative, we could just write them all as positives, but that won't always be the case. So just know there's always a second answer, in which case you've multiplied effectively the numerator and denominator both by negative 1. So here's what it ended up looking like. Question B in this section doesn't, escalate things too wildly, particularly with terms like 4y and 11x, but actually this first term here, x sine of y, is going to require some special attention. In particular, because we're multiplying x times some other function, we're going to actually have to use the product rule on that little section. So as a heads up, when we go to do this, the product rule will be involved. To start with though, I'm going to just start by writing my ddx part out. So we're going to do the derivative with respect to x of x sine of y minus 4y, and all of that will be equal to the derivative with respect to x of 11x Obviously, the right side's going to clean up really, really nicely into just 11 because the derivative of 11x with respect to x is 11. But on that left side, we do have to take into account that product rule part. So as I said before, we have two different functions here, x and sine of y. We're going to differentiate the x first, and we'll get 1 sine of y. Keep in mind that that's because the derivative of x is the same thing as the derivative of 1x plus 0, which is equal to 1. It's the slope of a line with slope 1. There's our first term. And then our second one, we'll have x times the derivative of sine of y. That's going to be cosine of y, but there was a y, so we need a y prime. And then last but not least, we also have to deal with the minus 4y. The derivative of minus 4y will be minus 4, but there was a y, so we do need y prime. And effectively, there is our implicit derivative having been taken. We just need to get y prime by its lonesome. Before I pursue that, let me just make one little point that sometimes students miss here. You look at this first term and you're like, wait, where's the y prime? Like we did a derivative and there was a y. We did, but keep in mind for that first part of the product rule, we were differentiating x with respect to x and then multiplying by sine of y. That sine of y did not get differentiated in that first term, so therefore there is no y prime. We were only differentiating the x part. So don't let your mind sort of trick you or gaslight you here. We're good to go. Now, having said that, I do got to get the y primes alone, so I'm going to subtract that 1 sine of y from both sides. Once I do, over on the left side, I can GCF out a y prime. We'll have x cosine of y minus 4. And on the right side, we're going to have 11 minus sine of y. And from here, just as we did before, we can divide both sides by whatever the other factor is. I'll divide by this pup. When I do, I am going to get that y prime, which is just a sort of sloppier version of dy dx. Not necessarily sloppier, but a slightly less intensely rigorous version of it. We will then get 11 minus sine of y divided by x cosine of y minus 4. And once again, there is our derivative, in this case with respect to x. So implicit differentiation, straight up implicit differentiation, you're differentiating with respect to a variable that's in the problem. There is our process taken into account. The last one I'm going to look at for tonight, just because I can feel the sort of exhaustion hitting a little bit, is question number 8. Question number 8 is one that I think I want to say that students not necessarily struggle with, but sort of psych themselves out with every single time. And that is that it's a related rates problem. These are the simplest, most straightforward versions of those related rates problems. But I'd be lying if I said that students didn't feel a little uncomfortable with them. Excuse me. So with that said, effectively what we're doing in this case is we're differentiating implicitly. This time, though, we're differentiating with respect to time t, a variable that's typically not in the relationship. And I think 8a is going to show us the process pretty cleanly. So I'm going to actually start there. I'll just start right in there, and you'll see the work in action. So our task in this first problem involves a square. We have the side length of a square is changing at 5 centimeters per second, and that's when its area is 36 centimeters squared. Our question is, at what rate is the square's area changing at that instant? And we're supposed to, of course, include units. So in here, there's a lot of stuff going on. I'm not going to lie. There's a lot of stuff happening in this particular case. So actually, I'm going to do a couple different moves here. Just going to add some colors so that way we have the potential to sort of see things in action. And actually, I think this should go together as well. So we'll go with that in red. So the first thing to note is we're dealing with a square. In fact, I didn't underline it, but we should underline that. We're dealing with a square. And in particular, there's mentions here several times about area and area. So what I want to note first is what is the area of a square? And of course, we know the area of a square as s squared, s standing for the side length. Now, having said that, there's this extra interesting piece of information right here that the area is 36 centimeters. So that's the measurement of that's our reference point. That's telling us when we're snapshotting this situation, when we're saying right about there. Tell me how fast things are changing there. Like we're saying it's when area is 36. And well, if the side length squared is equal to 36, I'm hoping you're okay making the leap to say that then the side lengths have to each be 6 centimeters. So in a sense, we're just getting some good information about the moment when we're trying to measure stuff. So there's our first move. The second piece of information is a little bit more subtle. It says that our area, the side length is changing at 5 centimeters per second. Since we're talking about the side lengths, this means this is going to be s prime. and specifically s prime is going to be 5 centimeters per second. So we've got some extra information here. Last but not least, as it says in red, we want to know at what rate is the area of the squares, or is the square's area changing, which means what we want in this particular problem, other than to be finished with it, what we want is a prime. So we're trying to figure out what is the rate of change of the area, given the information that we have. So our path to doing that is going to involve that geometric relationship that we gave in this case. What I'm going to do is I'm going to differentiate both sides with respect to time t, because things are changing with respect to t in this particular case. So that's where we're going to need to sort of dig our way in. So first of all, if we take the derivative with respect to t of a, we can call that dA dt, or just a prime. And on the right side, if we take the derivative with respect to t of s squared, the derivative of s squared is definitely 2 times s, but s is an implied function of time since s is changing, so we need to multiply by ds dt, also known as s prime. So fortunately for us, we already have some good information here. We have that s prime is going to be right there, equal to 5, and we likewise have that s is going to be 6. So effectively, we have a couple different values here. In fact, we could plug them straight into our equation and say that a is equal to 2 times, make sure to do this correctly, 2 times 6 times s prime, which is 5. And when we combine that stuff together, oops, I should use blue for this, we get 2 times 30, which is 60. As far as the units then, to finish this up, we're talking about the rate of change of an area. Area is measured in square units, so this will be in centimeters squared. And we're changing relative to time in seconds, so this will be centimeters squared per second. And again, the first version up here with all the colors, that's actually a super valid answer. You could absolutely have used that. So notice as we worked our way through here, our strategy was pretty straightforward. We generated the geometric relationship if it's not provided, and it wasn't here because we were talking about the area of a square. Then we use the given information to figure out what other information we are knowing, or we know what information is known in this particular case. And then effectively we differentiate it with respect to t, an implicit task, but a little bit different than the classic with respect to x implicit differentiation. And then we found our answer and reasoned out the units. So there is our process. This is a classic problem. I'd say that giving you the area instead of the side length has probably made this a little bit harder than the basic level, but this is still pretty low level as far as intensity, level of difficulty, the need for modeling things and sketching them out in really intense ways. This is a good, solid related rates problem involving I was going to say involving a solid, but it's not. It's involving a square or a rectangle. Square, excuse me. Well, that's a rectangle too. Okay, that brings us to 8b. I think 8b is a little bit harder than the questions that I tend to put onto here. I understand under a limited time frame, you have less time to read carefully, and forgetting things like the units really hurts you on an ESQ. But just wanted you to have this. This has been asked in the past. So in our situation, we have a 30-foot ladder leaned against a wall, and it's sliding down. So first of all, let's draw my ladder here. So there's my ladder. It's sliding down a wall. Let's draw a plum-colored building here, because why not? And then we'll have the road it's sliding down. The road is green, either because it's covered in ooze or because it's grassy for some reason. But in any event, as you can hope, we're going to assume that this building, we'll make that assumption. We're going to assume this building is perpendicular to the ground. Otherwise, the entire thing involves the law of sines and cosines. Good luck with that. Excuse me. So from here, what comes next? Well, what comes next is going to be us labeling the things that are changing and labeling the things that are not. And one of those things that is not changing is going to be the length of the ladder. That's going to be 30 feet consistently. It's not changing at all. On the other hand, as the top moves down, the bottom moves out. So both of those two are changing. That's actually really hard. So if I can do this. That sort of worked. I sort of executed it. Yeah, I'm proud of myself too. So as far as each of these pieces, since they're both changing, I'm going to call this X, and I'm going to call the other one Y. Actually, I should use a different color for that. We'll call this Y, X and Y. Y, by the way, is only going from there to there. And then finally, since both of those are changing, we do know their values at specific instance. It mentions that the top is 24 feet up the wall. So I can label on the inside that that height is 24 at the moment we've snapshotted and that we're interested in the rates of change at. But you'll notice that we're missing X. So before we can dive into this problem, it's worth trying to figure out if we can figure out what x is equal to. So we can do that using the Pythagorean theorem. So this will be the same thing as x squared plus y squared equals 30 squared. But notice that we do in fact have 24 there. So x squared plus 24 squared is equal to 30 squared. Now, as a heads up, I can tell you what this is going to lead us to. It's going to lead us to x equals 18. You don't have a calculator on this one, which I think makes this problem a little bit tougher than it probably should be. Sorry, there's a gnat on my screen. So just as a heads up, what I'm seeing here is that these are multiples of the 3, 4, 5 right triangle. This is 4 times 6. This was 5 times 6. So I'm anticipating x would be 3 times 6. So there's lots of ways that you could actually formally show this to verify that this is in fact correct, but I'm just going to ask you to trust me. Like I said, this one doesn't fit as an ESQ, but I think the ideas and preparation is really good. So with that in place, we now know that this length is going to be 18 at the instant in question, and now we can bring all this information together. So to capture what's changing, I'm going to write out the Pythagorean theorem one more time. This will be x squared plus y squared equals 30 squared. And then just as we've done several times before, I'm going to differentiate with respect to t. So spilling the t on related rates problems, differentiate with respect to t. You know it. So when you go to differentiate, the right side's easy. It's going to be 0. 30 is a number, so 30 squared is definitely a number as well. In fact, it's 900. That derivative is 0. On the left side, though, we're going to get 2x times x prime, because x is connected to t, and 2y y prime, all equal to 0. So now, given this information, we can start plugging in things and cleaning this up a little bit. The first thing I like to do is I like to divide both sides by 2, just to clean things up a little and give us less factors to kind of keep carrying around. The second thing, though, is I'll plug in values. So 18 is going to be x. X prime, it says the base moves away from the wall at 2 feet per minute. So I'm going to then multiply by 2. The reason it's positive 2 and not negative 2 despite moving to the left is because that length at the bottom is getting wider. So if something is increasing, its derivative should be positive. Something we learned in Unit 3 of last quarter. Or, excuse me, Quarter 3. Unit 3 of the first quarter of Calculus AB. Sorry, I taught Calculus AB all last quarter. It's in the back of my mind. On the other side, we know y is 24 specifically, but we don't know y prime. But we're going to find it. We're going to find it. Gosh darn it. So from here, I just need to solve for y prime. It's pretty trivial. This will be negative 24, 36 over 24. So negative 36 over 24. If I divide out the 12, I get negative 3 over 2. So what that tells us is that the height of the ladder along the wall is getting smaller. That makes sense based on what we said. As it gets lower on the top, it's going to get further and further out. So, y prime, oh, sorry, we did that backwards. As it goes further and further out, the height gets lower and lower. So yes, this should be negative. And then our units, they're going to be measured the same way as x's units are. They will be in feet per minute. You could also, if you didn't like having that negative sign there, you could say that the height of the ladder along the wall was decreasing at 3/2 feet per minute, or 1.5 feet per minute at time t equals this one. So there goes another one. And then finally, the last one I'm going to do for tonight, because that'll allow me to go to bed a little bit earlier while this renders. Actually, OBS renders really fast. It's kind of nice. So what I'm going to do on this last one, this one's sort of the stripped down version. There's a lot going on, but this one doesn't feature the sort of geometric appeal. It doesn't feature any requirements for you to know particular relationships. It gives you a relationship. There it is. I'm going to say it's like one of those dating shows. It just gives you a relationship and goes, here you go, do things. Pretty sure that's how dating shows go. I don't think I've watched a single dating show outside of the first episode of The Bachelor ever. I think I watched that whenever it aired. What was that, like 2007? Weird thing to have in an ESQ model video. That's fine. I don't care. I'm not going to change it. I'm too tired. So they give us our relationship, and then they give us several values or expressions that are with respect to t. So you don't have to tell me once, or you don't have to tell me twice. You do have to tell me once, otherwise I won't know what to do. We're going to take the derivative with respect to t of x to the fourth plus 5y to the third. All that's going to be equal to the derivative with respect to t of z. TMZ? No, that's not related to Bachelor. I have no idea. I'm at that loopy phase at this point. I just want this complete. But I'm going to get it right. I am not going to remake this video. So differentiating with respect to t, on the left side, the derivative of x to the fourth is 4x cubed, but we need that x prime to account for the fact that x is changing with respect to t. In fact, there is x prime right there. Next, we have 5y cubed. That's going to be 15y squared, but that y with respect to t requires us to multiply by y prime. And then finally, on the far right side, we're going to have z prime, just one z prime if you so desired. So we have x prime, we have y prime, and then we are specifically provided at this moment x equals 2 and y equals 5 when those are the values of x prime and y prime. So let's plug them in and see what happens. So we have 4 times 2 cubed times 10 plus 15 times y squared, oh that's large, times y prime, which is negative 3, and then all equals z prime. This looks like a great candidate to not simplify things, but that's okay, we can do it. 4 times 8 is 32. Oh, times 10 is 320. On this next one, we're going to have negative 45 times 25. I've got a strategy for this, don't you worry. And then all of this is equal to z prime. So it's going to be very negative, it looks like. Like me after not getting enough sleep. Going to be very negative. What I'm thinking for this is me just sort of doing one of those appeals. Since this is a no calculator question, like I said, this could be a little bit tough just because of the numbers. But what is negative 45 times 25? Well, 25 is 100 divided by 4. So my theory here is if I multiply this through, negative 4,500 over 4. I can now separate this. This is literally how I do things, by the way. This is how I do these things in my head. If you've ever been curious how I do it, here's the things that happen in my head. I'm just narrating them out loud. So there's that first one, and then plus, it would be negative 500 over 4. So in this case, this is going to give me negative 1,000. Again, all this for just the arithmetic. By the way, just box this as your answer. Just stop. Just box the answer. But completing this, I'm going to do this right. So minus 500 over 25, that's going to be minus 125. I'm doing that as 500 over 2 is 250. 250 over 2 is 125. This is minus 1125. So we get 320 minus 1125 equals z prime. Geez, no, I don't want to do more. Okay, so once again, you're watching my brain in action. This is all so much overkill, I'm sorry. I shouldn't do this, but I have so little confidence that people actually use these ESQ videos that I think it's fair for me to indulge myself in a little bit of number sense here. So what I'm doing is I'm decomposing all those things you did in elementary school that you were like, when will... No, you wouldn't have said it like that. When will I ever need to do this? You would have been like, when will I ever need to use this? What? Why did I sound like a parrot? I have no idea. In this case, that's going to be negative, let's see, if that's 1120, that's going to be negative 800 minus 5 equals z prime. So z prime, also known as dz dt, is equal to negative 805, it looks like. Now, to be honest, I'm not sure if that's correct. So let's check this really fast. Okay, let's check it on Desmos. Come on, Desmos. Let's see what we got. Did I get the right answer here? All this work just to check arithmetic. That's fine. So we have 320 minus 1125. Oh, it's minus 805. Yeah, I got it. You're not watching anyway. So yeah, I'm going to stop right there. I got the answer. Yeah, that's a ludicrously large number. I should change it because I haven't posted it yet. But I'm not going to, because you don't have to simplify. In which case, that protects me from any sort of bad answer. If you don't want to write it or do the arithmetic, or I'm bad at arithmetic, cool. That's great. You don't have to simplify it in here. That's the AP Calculus exam rule, so we follow that rule as well. We also follow the rules that say I get to go to bed, and I'm going to go to bed. So I'm calling it a day. Thank you for watching. Hopefully you got some good value out of this. I think we only did 3 questions, but hopefully they were an important 3 questions. So I think that we'll make it after all. Farewell.